We will start with this session where we will take it forward from the previous session in a sense that we talked about diffusion type of problems. That means the problems where if you consider the general transport equation, there are 4 different types of terms. One is the unsteady term, another is the advection term, another is the diffusion term, and another is the source term or generation term. So, we have seen so far problems or scenarios where you could have the unsteady term, the diffusion term and the source term. One classical example that we have covered is unsteady heat conduction equation, but that did not have any fluid flow. So, advection, which physically comes from the acceleration of the fluid, that will bring in the transport of the physical variable via the flow of fluid. Like if you have heat transfer, then heat can get transported with the fluid flow from one place to another place. Although we loosely call it as convection, this is fundamentally known as advection, and advection plus conduction is known as convection. So, convection cannot take place without conduction, like heat transfer. Similarly, you have mass transfer, etc. So, why convection cannot take place without conduction? Let us say you have a hot wall on which a fluid is flowing. So, how can the heat get transferred from the hot wall to the fluid? That is only by conduction, and then from there it will be transported within the fluid by both conduction and advection. So, in that way conduction is a must for such a scenario where fluid flow is influencing the transport of heat and very similar other applications. So, overall the scenario is you have convection because you have fluid flow, and you anyway also have diffusion. Diffusion of heat is conduction. So, in that way in a general terminology, this is called as convection diffusion problem. This is just a name. So, what we will now see that in the convection diffusion problem, we will add the fluid flow effects, and when we add the fluid flow effects, what is the implication in your solution. So, when you add the fluid flow effects, the question is how do you know what is the velocity, because let us say you are solving the energy equation where the convective transport of heat is taking place. So, what does it mean? That you have a change in temperature where the fluid velocity also plays a role. So, if you are solving or trying to solve for temperature from such an equation, you have to substitute the value of velocity, only then you can solve for temperature in that equation. So, question is where from that velocity will come. So, that is what is the numerical solution of the fluid flow equations that we will study in the next session, but for this session we will assume that it is known from somewhere. So, if it is known from somewhere, then how can we use that to solve for other variables like say temperature for example. So, let one such variable be phi. So, whatever we had the previous example where we were talking about the diffusion problem, the temperature and thermal conductivity, those are sort of generically replaced with some variable phi and some diffusion coefficient gamma, and that means that you can cast the general equation, and we have seen that how this can be derived from the basic conservation principle, that we can cast the equation in this form, and the velocity is of course to be solved from the continuity and the momentum equations, and we will assume that they are solved, and therefore, in the equation which is written in the box, velocity is known. So, the problem that we are trying to address is if u, j they are known, then how to solve for phi. Okay. Now, any problem, as we discussed, that any problem to understand it fundamentally, it is always good to start with one dimensional. Sometimes it may appear that one dimensional is too simple, but if you are looking at fluxes, so you have a surface and flux is always normal to the surface. That means the flux gives a local one dimensional effect of what is happening, although overall it is 3 dimensional in general. So, if we understand the one dimensional problem and from that we understand how to treat the fluxes, that concept we can readily extend to 2D and 3D. So, as usual we have constructed a control volume. The nomenclature is exactly the same what we used for the diffusion problem. So, one dimensional version of this means you have only x direction and steady. Unsteady we are not bringing it here, because unsteady term, how to treat it, whatever we have discussed for the diffusion type of problem, it is same for all types of problem. That is, you have those explicit, implicit, Crank-Nicolson, those types of schemes. So, that is not dependent on whether advection is there or not. So, we have not kept the unsteady, and we have also not kept the source term, because source term, how to discretize it we have seen. Again, that does not depend on whether it is fluid flow problem or not. So, what special feature we have added is that had there been no fluid flow, the left hand side would have been 0. Now, you have a left hand side ddx of rho u phi. Okay. So, once you have that, of course, this is such an equation which has analytical solution. Anyone who is looking into this will argue that if this has an analytical solution, why are you talking about it for a numerical solution? Now, this is where you have to develop your maturity of how a subject is developed. Always when you develop a subject, you try to standardize it with respect to something for which you have a very comprehensive knowledge in hand. So, this particular scenario, although it looks like a very simple scenario, it will enable you to standardize the algorithm, which you can extend it to more complex scenario where you do not have such a simple one dimensional equation. And the continuity equation also along x, if you have that, you will have ddx of rho u equal to 0. There is no y or z variation. So, now with this we will try to see that if we want to discretize it, so what we would do. So, look into the previous slide. So, what would you do? Your step is, the step 1 is integrate the governing differential equation over the finite control volume. This is the first step of the finite volume method. So, if you integrate this ddx and then dx and integrate it, that means d of rho u phi, integrate from small w to small e, then what you get? Rho u phi at small e minus rho u phi at small w. Right hand side is diffusion, and in fact for diffusion we have seen how to treat it, and that is where we start with our first sort of scheme or first method of discretization. So, we have used this piecewise linear interpolation for the diffusion terms for our diffusion problems. So, if you recall, for the diffusion problems we assume that phi varies, or in that specific example temperature varies linearly between two grid points, and that is what we have drawn here. So, in that case the right hand side is just a difference equation, because if it is linear, it is d phi dx is phi p minus phi w divided by x p minus x w, that is delta x e. So, in that way right hand side you can write, and although it is a linear interpolation, in terms of finite difference it is just like something which we call as a central difference scheme. So, in what we are trying to do here, and in fact this is something which is quite interesting, that when we are talking about the central difference, forward difference, backward difference, etc., in finite difference, they are all different linear forms of interpolation, only between which two points you are interpolating, accordingly you will have the name of the scheme. So, in a way, whatever is the method, either directly or indirectly you are approximating the function by another function, in this case a polynomial linear polynomial. Now, the main focus here is the left hand side, because this has now appeared as new to this problem. So, if you have this say small e at the midway between capital P and capital E and it is linear, then phi at small e is half of phi at capital E plus phi at capital P, right, because it is a linear variation, and similarly phi at small w. So, that is what we have written, because our objective is that in your left hand side expression small e and small w values are coming, but your variables which you are solving are based on the main grid points, that is capital P, capital E, capital W, etc. So, that requires interpolation, and here what we are doing is whatever profile we have used for the diffusion term, the same we are using for the this so called convection and putting up that interpolated value. So, you will get then again of the same form AP into phi P equal to AE into phi E plus AW into phi W. See, that is why I emphasize so much on learning how to solve the system of linear algebraic equations, because you will get a similar system no matter whether your fluid flow is there or not, only coefficients will change. So, you have these coefficients AP, AE, AW, etc. So, one very obvious observation that you can see, that if u is positive along the x direction, then AW, so we have assumed that delta x E and delta x W are all the same, and that is equal to delta x, just to write simplified form. So, you have AW, it is positive because all other things are positive. So, by one of the basic rules, all coefficients should be of the same sign, but AE there is no guarantee that it will be positive. So, it all depends on whether gamma by delta x is greater than rho u by 2 or not. So, that means that for this scheme to work, what you need to have. So, we have taken as an example delta x E equal to delta x W is equal to delta x. So, your rho and say gamma E is equal to gamma W equal to gamma. Let us say this all are the same. So, then your AE will be equal to gamma by delta x minus rho UE by 2. Okay. So, you want it to be greater than 0. Okay. So, that means you want rho UE by 2 less than gamma by delta x. So, rho UE divided by gamma by delta x less than 2, right. Why I have written it in this way is because this represents what? This represents the strength of advection. So, if you multiply say both numerator and denominator by phi, so this is the strength of transport of phi due to fluid flow. So, more the velocity, more will be the transport. So, it is quite intuitive, say you have very strong wind blowing over a surface. So, if there is some heat, faster the wind is blowing, faster it will carry the heat. So, that is this strength of advection, and this one is the strength of diffusion. Okay. So, because this is like k by delta x, so it is like conductance for heat transfer. So, this is advection strength and this is diffusion strength. So, you have this is as a physically it means advection strength by diffusion strength. So, that has to be less than 2, not globally, but based on this length delta x. So, this ratio of advection to diffusion is known as Peclet number. PE. So, for a physical problem, if say L is the length of the length scale, the Peclet number will depend on the length scale L, but this is not the overall length scale of the domain, but only for the cell or control volume. So, this is called a cell Peclet number. That means Peclet number with respect to the dimension of the cell or the control volume. So, you can see that this is like a conditionally stable scheme where your delta x. So, if you see what is its value coming? Its value is coming is rho ue into delta x by gamma. So, this has to be less than 2. So, what is there in your hand? In your hand, see, rho is not there in your hand because it is the density of the fluid that you cannot change at your will. So, this is fixed. Velocity you have already got from the fluid flow equation, whatever is the solution, that also is not there in your hand. Gamma is like that, say thermal conductivity etc. So, that is a property of the fluid, that also you cannot change. So, the only thing that you can change is delta x because it depends on your choice of the grid. So, here you see that there is a restriction in this, just like you had a restriction in the time step in the explicit scheme, you have a restriction in the grid spacing in this central difference scheme. So, this scheme works good so long as you obey this restriction. So, one way is to make it so fine that it will always be satisfied, but that also you cannot guarantee because a problem can you can have varying properties, varying velocity. So, when it will be satisfied and when it will be not satisfied, that you do not know, even though if you make delta x very small. So, this can go out of your hand in terms of giving a physically realistic solution, and that is why the central difference scheme, typically although very appealing, we do not normally use for solving the convection diffusion problems, unless we are absolutely sure that this is going to work for all cases. If you are absolutely sure, it is quite simple because it is a linear interpolation. So, that is what makes this restricted. So, we should go for something which is very different. Now, if you understand physically that when there is a chance that this can become large, so maybe density or gamma and delta x, so these you have fixed, but when you are running different problems, different situations, this u can blow up, u can be large, you can have a large velocity, and if you have a large velocity then it will blow up. So, the large velocity situation or beyond the threshold value, so that this is not satisfied, is your vulnerable situation. And large velocity means actually what is happening, that you have a fluid flow sweeping the entire thing quite fast from the west to the east, that is what is physically happening. So, if such a situation comes, we know that this is not likely to work because u being large, it may become greater than 2. So, let us try to develop a discretization scheme by keeping that as a possible scenario for deviation from here, and that motivates to the development of this, which is known as upwind scheme. So, in the upwind scheme, so what you see is just see this simple picture. I mean, I will try to make it even simpler by drawing simpler schematic on the board, and then possibly you will understand it more easily, and then we will refer to the slide for just the algebraic part of it. Conceptual part I am trying to explain here. So, let us say you have this one dimensional scenario, you have the capital P, then you have capital E and you have capital W, and this is your small w, this is your small e, and you have a say high speed unidirectional flow like this. This is the physical scenario we are just thinking about. So, where was the vulnerability? The vulnerability was interpolating the left hand side by a function which is a linear between the two grid points. So, what are your possible choices? Of course, overall thing is you have to change that interpolation. So, how can you change that? There are two ways. One is you can change that to a more complex variation, or you can change that to a more simple variation. So, usually people who are not familiar with how scientific topics are developed will try to go for complexification, because the general understanding is that more complex the thing is, that should capture more complex scenario also. But the beauty of science and beauty of any advancement in a subject is that all major advancements have taken place where maybe a complex scenario has been represented in a very simple way. Just diverting from here, we have learnt many equations from our school days. Now, very early in say the school level science, when the mathematical forms were there introduced, we have learnt about that E equal to mc square, Einstein's thing. Now, you cannot have any such a complex theory leading to such a simple equation. Usually if the equation is so simple, our intuition is that the concept also is very simple, but that mass energy equivalence is not that simple a thing, it is not intuitive at least, or it was not that intuitive at the time when Einstein was working on it. But the beauty of it was its simplicity. So, one has to understand that if you see pages of equations written, that does not necessarily mean that it is glamorous. You have to see that what is that essence that it is carrying, can you simplify it to an extent. So, this scheme tries to do that. So, what it says that if UE is greater than, so let us concentrate on, let me try to use another color. So, let us concentrate on here. So, you have something as UE. So, your objective is to write an interpolation for UE in terms of P or E or a combination of that. In the finite, in the central difference, it was half of whatever was used, it led to this half here plus and half of this plus this. So, now not really U. So, overall rho UE, say rho E UE phi E, because UE already your main interpolation challenge is phi small e, okay. So, what it says is that if it is a strong unidirectional flow, then you have phi small e equal to phi p if UE greater than 0. So, what it is simply saying that if the fluid is flowing very fast and along this direction, then whatever is the value of phi here, it is mostly due to this. That means the upstream motion is influencing it the most, and it is quite logical, because the downstream will try to influence more and more when you have diffusion also in the opposite direction influencing. But if the Peclet number is significantly large, then the diffusion from the other side is not going to influence that much. So, the value of this is strongly influenced by value of this, and that is the expectation of this scheme. So, instead of linear, it is just like a constant, even the simplest form of linear. And if it is the other way, that means you have fluid flow in this direction, then it is phi E, that means because it is then coming from capital E to small e if UE less than 0, okay. Now, if you want to combine these two in the form of a single statement, so that is what is written here. There is a function this a comma b with this angle bracket, it returns. So, you can say it as max of a and b, maybe you can define or such functions are there inbuilt as in many programming languages. So, this will return out of these two whichever is larger, it will return that. Okay. So, look at that. Now, look at the first expression that is written. So, what it does is basically combines these two different steps into a single. So, it says that rho u phi e is equal to phi p into max of rho u e comma 0 minus phi e into max of say minus rho u e and 0. Okay. So, if you take the first example that u e greater than 0, if u e is greater than 0, then max of rho u e and 0 is rho u e, right, and then max of minus rho u and 0 is 0. So, this will return 0 and this will return rho u e. So, effectively phi small e will become phi capital P. On the other hand, if you have u e less than 0, then out of rho u e and 0, 0 will be maximum. So, that this term will be 0, and then out of these two, if u e is negative, this will be greater. So, that will be returned and this minus will make it plus. So, phi small e will be phi capital E. Okay. So, that is nothing but a very neat coding way of combining these two together in the form of one statement. And similarly W, I am not getting into that because it is the same, just your points have changed, grid points have changed. So, then what you are doing is you are now putting this new interpolation, what is there at the top, in the left hand side, and right hand side you are still using the linear. Why? Because right hand side if you put a constant, the derivative will be 0. So, you cannot capture the dt dx or d phi dx. Now, this is one strength of the finite volume method, that for different physical terms you can use different interpolation or different approximating functions, which is usually not the flexibility for any. Yes, tell. No, whether it is negative or positive is different. So, your objective is to reproduce phi small e is equal to phi capital E. Value algebraically whatever it is, you have to look into symbolically, okay, because you really do not, even phi can be positive or negative, that is a different thing, okay. So, we have to see that whether this particular expression is reproducing this, that is it, okay. So, now if you are putting the values here, you will see that you have now got a scheme where in the left hand side you have effectively taken it as a constant value at a particular grid or a node, and right hand side a linear variation, piecewise linear variation. So, this is called as an upwind scheme. Now, this is, there can be many variants of the upwind scheme. This is like you have taken just maybe one point, say these 2 points to describe the upwind. Someone may take, for example, say you have this point E. So, the value at E, someone may take that it is influenced by not just P but maybe also at W, because if that will represent more effect of the upwind grids. But if you take 2 points, it will become a quadratic. So, more points you take, See, this is like basic maths of interpolation. So, more number of points you take means you have more unknown coefficients. So, more unknown coefficients can be accommodated only by higher and higher order polynomials. So, more number of points you take to build up approximating function, maybe your approximation is more accurate, but the cost that you have to pay is that you are working with higher order interpolations, and that also may not always be accurate, because who knows that when you substitute that it may violate one of the basic rules out of the 4 rules. So, the moral of the story is, if we can keep it simple, let us keep simple. So, if we do it like this, now you have the coefficients and you see that you are always using a max function. So, the max function is not returning anything in these two cases, not returning anything which is less than 0. If the thing is becoming negative, the max function is returning 0. So, you do not have any chance of any coefficient becoming negative. Okay. So, it is satisfying the basic rules. But having said that, you have to keep in mind that this is the other extreme of the previous case. The previous case, we like the central difference scheme, it would work for low Peclet number. That means advection strength is much less than the diffusion strength, and this will physically be very good if it is high Peclet number, because it is almost like the high velocity sweeping the entire thing. So, the two schemes are as if keeping in view about physical scenarios of low and high Peclet number, although you can apply it for any case, but they will physically be matching with those situations. In reality, you may not have either very small Peclet number or very large Peclet number. So, then it may not be a bad idea to see that in reality, if you have say a situation where you are just keeping the Peclet number as a parameter, neither large nor small, and try to see that how your solution is there for the limiting cases of very small and large Peclet number. So, to do that, this one dimensional equation, only this one dimensional form can be analytically solved. So, you can solve this analytically, and it is an exponential form. It is quite easy to do it analytically. If you just put the boundary conditions and the solution is given, and how the exponential form comes is because you have this d phi by phi. So, if once you integrate it, it will be ln phi. So, then that phi will be e to the power something, and that is what that exponential form comes. So, this is the exact solution. In fact, someone can use this exact solution as a approximating function. You can say that if it is exact, why then you are calling it as an approximating function? We are calling it as an approximating function because let us say you have even a one dimensional problem. You have the values given these 2 points, but say there are in between 2 points and you are applying this solution. So, these boundary conditions are not known. So, if the boundary conditions are known, then this is the exact solution. But if these are not known, so you cannot call it like exact solution, but overall the trend will be very similar. But if it is 2 dimensional, 3 dimensional, this will not be the exact case, but this is a good motivator to develop an interpolation function. But nobody uses this in practice, knowing fully that this is going to be very accurate. So, in fact, if this is put into that your left hand side phi small e and phi small w, and then it is integrated, then you will get some discretized form. But people will usually not like to do it because you have exponential calculations, and exponential calculation, that is e to the power calculation, in computation is quite expensive, because you have to calculate a large number of terms of the exponential series e to the power x. Okay. So, in that way, this is always a golden rule for computation, that we should try to avoid such exponential calculation. And another challenge with exponential calculation is that the e to the power, that argument, if it is large, then exponential can blow up numerically. So, in that way the exponential scheme, there is a so called exponential scheme. I am not getting into all the schemes because it will be then like a full 1 semester course. You can again go through my NPTEL lectures, but I am trying to give you the in between line understanding of how these algorithms have been developed. It is very important to know this because see, there are two ways in which students learn a subject, and we have also been students. Say there is a geometry, and if say in junior class you are told that construct, take line AB, draw a perpendicular to that at the point D, then draw an angle this, and you are faithfully doing that, and then you are solving a problem, and then also you learn it. But the learning, the challenge of that learning is, if you are not thinking by yourself why I should draw that perpendicular, then that remains unanswered. So, then you become mechanical. Whatever is already there in the book, you can learn it and produce it, but when innovation is expected from you, you do not understand the philosophy of innovation, then you cannot do any new thing. So, if you are developing a new algorithm, you must appreciate how the previous algorithms were conceptually developed, one from the other. That will give you the training of being innovative in developing new algorithms. See, innovation does not come out of magic. These days people say someone is very innovative. So, innovation does not come out of magic, it is not common sense. A lot of training where you are trained to think is going to give you innovation. So, this is not more of like what scheme is written in the book and that is reproduced with integration and differentiation, that is not the spirit. The spirit is how it trains us to develop from one algorithm to the other. So, you can see that if the Peclet number is 0, then it is like the central difference scheme, that linear. That means for low Peclet number it is fine, and if the Peclet number is large, much less than -1 or much greater than 1, in both cases the magnitude is large, you can see that it is very nicely reproducing the upwind scheme like a constant. But if it is in between, then there are ways of say representing this exponential function by some low cost function. Low cost means computationally low cost. So, what can be done? You can maybe say, there are many ways to do it. So, let us say you have an exponential function like this. So, you can represent it possibly by maybe one tangent like this, maybe another tangent like this, and maybe a asymptotic constant, because say exponential decay will being a constant. I am just giving one example. So, it may be possible, so forget about this intersected part. So, you can combine these by say 3 different linear functions and make sure that they are continuous in value when they join. So, this is a representation of a complex function, not complex in a sense that it is really very complex, but complex to compute, to some simpler functions which are easier to compute, but not maybe one such function will do, but you can make a piecewise linearization and then combine it. So, such a scheme is there, it is known as hybrid scheme. But sometimes exponential also can be represented by approximately not e to the power form, but a function with a certain power. So, that may give an approximation, and Professor Patankar found that with some value of that power, it closely reproduces this one, and that scheme he gave a name power law model. So, all these are motivated by the fact. So, if you see now the summary of understanding. So, we started with the finite difference or central difference because that was the intuitive thing that we were carrying from the diffusion problem. We found that it has a problem. Then we went to a physical appeal of, well, the problem was that if the flow is strong, then Peclet number would be large, and then there is a problem. So, we found out a solution if the Peclet number is large and it physically reproduces by the upwind scheme. But in reality, when it is in between, it is exponentially represented in a nice way but exponential calculation is computationally expensive. So, there may be more simplified forms of doing it through other forms of interpolation. One is that piecewise linear, which is the hybrid, and representing it by a power law is the power law scheme. Okay. So, this is all about convection diffusion problem. Now, maybe we can get into say 1 or 2 examples, the review questions. So, let us say that you have a condenser in which you have the temperature variation. So, the left hand side is the mass flow rate into specific heat into rate of change of temperature. So, this is like you can say the advection, and the right hand side is the rate of heat exchange, which is U is capital U is the overall heat transfer coefficient into capital A by L into T naught minus T, where T naught is a reference temperature. See, for solving this problem you do not have to really understand what it is physically, but sometimes if you know it, it is good, but at the end it is a mathematical problem. So, what you are asked to do is define a non-dimensional temperature, theta is T minus T in by T naught minus T in, where T in is the inlet temperature in the heat exchanger, and you use a non-dimensional x and call it y equal to x by L, and you take 5 grid points and use the upwind scheme. So, this kind of question sometimes we give in the exam to recognize that, see, there are 2 ways we test that how a student has learnt a subject. One is that you give the scheme algorithm, student can mechanically write the code with those things given, replace P by I, E by I plus 1, W by I minus 1, and write a code. That is mechanical, that means even if you do not understand what it is, from the formula you write. But the other is, do you get a physical feel of what it is? So, this is such a test. So, I always prefer that this is the test, this kind of thing everyone should do before getting into the computer exercise, at least 1 or 2. So, if you look into this equation, so when we have replaced the temperature with that non-dimensional variable theta, then we have come up with that equation, that means d theta dy is equal to 2 into 1 minus theta. So, that is just algebraic manipulation. So, your objective is discretizing d theta dy is equal to 2 into 1 minus theta by the upwind scheme. So, if you now, so first is finite volume, means you have to integrate it with respect to your control volume. So, your variable is y. So, you integrate it with respect to y. So, you now have d theta dy. So, you have theta small e minus theta small w, that is d theta integrated from small w to small e, and in the right hand side it is just like a source term. So, you may take this theta say equal to a constant which is theta p, and then you can take that out of the integral. So, integral of dy will be delta y. So, now you have your equation where you have a discretized equation. You can write it as this AP into theta p equal to AE into theta e plus AW theta w plus B. There is a B because there is a source term. Here it is a sink basically, maybe heat is lost. So, with all the values given, so you have 3 equations, and these 3 algebraic equations, in fact 4 equations, because you have 4 grid points, you can solve them and you can get the values. Very easy to solve them, even by hand calculation. And exact solution you can also find out, analytical solution, d theta dy plus 2 theta equal to 2. So, you can get the analytical solution, and with these values if you make a graph of the numerical and analytical, it will give you a complete picture of what your scheme is doing. Okay. And you may vary the parameters and see for which parameter your scheme is doing well and for which parameter your scheme is not doing well. So, these kinds of things, these may look to be very simple, but this is really the understanding of the subject. So, we close this particular chapter, and maybe we take a short break of about 5 minutes, and we will then get into the next chapter, which is the next session, which is the fluid flow problem. That means numerical solution of the Navier-Stokes equation.